Hi everybody, my name is Hamza and I conduct my research as a PhD student in a collaboration between IBM France Lab and the Computer Science Department of Université Pierre-Marie Curie. For your information, just recall that IBM France Lab is the former ILO company which is acquired by IBM and which is also well known for the two products, Cplex and Shores. So I would like to begin with motivating our research. So our motivation is driven by the need to integrate uncertain reasoning and representation inside business rules. This uncertainty may be caused by our imperfect judgment, measurement errors, or imprecise in gathering information in the data. So, for example, we want to be able to, in such context, we want to be able to run the Boolean first rules, which familiarly state that we display an alert whenever a subscriber's age is less than 11 and we have the reimbursement type is less. And in the presence of such kind of uncertainties, we want to still have the possibility or the capacity to run such rules. So we want to introduce a probabilistic operator and some attributes, here for example the risk attributes, that may somehow represent the relation that link the attribute age and the reimbursement type. So this is the outline of the presentation. After introducing the necessary background, I present our approach to deal with uncertainty in business rules management, and I present also how we apply it to the IBM product, and then I give some conclusion and perspective at the end. So let's go on. As you may know, that business rule management systems are very popular tools for decision management system, for decision making automation, because they allow non-professional non-IT specialists, which are professional business, to collaborate with IT professionals without being a computer scientist. So this is the major things that make them very popular. So they allow collaboration between non-specialist and IT specialist. And in these tools are well adapted when we deal with structured and complete data. But in front of uncertain or incomplete data, these tools face some difficulties, and commonly in the domain of artificial intelligence, people use there are many approaches to handle such situation. Here are such just the most commonly used. For example, the heuristic models that try to weight rules with certainty degrees of certainty or factor or degrees of truth. We can cite here the certainty factor or ratio or likelihood ratios. These are about uncertainty of the knowledge, that is the rules and not the data. And fuzzy logic also that try to handle or capture uncertainty related to imprecise that can be in the rule. Another approach is the probabilistic graphical models, PGM, with the twofold, the directed fields, which are Bayesian networks, and the undirected one, which Markov field, random Markov fields. In particular, we are interested in Bayesian techniques. The final one is probabilistic logic programming, and for instance, problog program, which are an extension of logic programming to probabilistic knowledge, just by weighting rules with facts with probabilities. And in our case, we will be using PGL to deal with uncertainty because they are mathematically sound and well-established framework to deal uncertainty in the domain of artificial attribution. And also because they allow us to define relationship between different objects in the domain, and because they support the object-oriented paradigm, and also they find many applications to modern business rule management system, which basically are nowadays based on the object-oriented framework. So let's give a brief overview of what is a BRMS, a business rule management system based on object-oriented paradigm. Business rules here are production rules, as you may know, of the form if condition then action. It may have an else part, and they execute the rules against an object model, which describes the application model data. And here we illustrated through this very simple example where we have three classes and healthcare provider that may be related to a class of subscriber that contains a set of reimbursement. And here we have an example of a business rules that basically state that we will run or raise an alert when we have a healthcare provider having a subscriber whose age is less than 11 and with a specific type of reimbursement, which is here the LEDs. We should know, as I mentioned earlier, that this type of rules are well handled with current state of business rule management system. But in case of lack of information or knowledge about, for example, the age or the types, we're a little bit stuck. We cannot run such rules in current business rule management system. So to handle this issue, we want to introduce a coupling approach with probabilistic relational model, which are an extension of Bayesian network to object-oriented paradigm. I assume that everybody is familiar with Bayesian network techniques. And let's give an overview of probabilistic relational model. So the basic idea is that in complex system, one may identify repeated patterns that can be abstracted in classes. Classes here are just a fragment of Bayesian networks over a subset of random variables of the system. And each classes contain the definition of relations between attributes and the definition of the condition probability tables. And for example, for the class E, everything is okay because every attribute is inside the class. But for the class F, we have the attribute U that depends on outside attributes. That's we introduce the notion of reference slot to allow us to navigate between attributes from different classes. So our initial system can be seen as an instantiation of these two classes. So we have two instantiations of the class E and three instantiations of the class F, and with a specification of the relations between these classes, and we have a compact representation of the initial system with the relation skeleton. The class, the instance E2 is related, for instance, to the instance F3. And here is a possible representation of our running example in a PRM framework. Here we have three classes, and we have the reimbursement reference slot, which is in our case here is a multiple reference slot that relate the subscriber to a set of reimbursement and we have a healthcare provider, which is related to a set of subscriber. Also here it is a multiple reference slot. We will see later why we added these. Let's call them auxiliary variables, exists and type risks. So, and this is an example of an instantiation of our classes. For example, we have two subscribers related to one healthcare provider here. So, we can highlight from this point the common oriented object paradigm that is shared with PRM, probabilistic relational model, and the object model against which business rules management system are executed. And not only this, probabilistic relational model also define relations between different classes. That's why we choose to perform a coupling approach. In other reason for this coupling approach, that we are dealing with different operational semantics. Basically, on the one hand, we have the business rule engines that are procedural and non-monotonic on the data of the working memory, for example. And on the other hand, we have probabilistic relational models that are mathematic frameworks, that they have their own algorithm to execute, and maybe they have their own life cycle for data. So we want to separate both framework to control the complexity of both sides, and to facilitate, by the way, the maintaining of the softwares to have a better performance. For this reason, we propose to have two extensions for the business rule models. So we want to add some attributes to the missing attributes. For example, the risk attribute that we showed before, and to have some annotations that will incorporate the probabilistic informations, and from which we can generate by later our probabilistic relational model and execute inference. And finally, to give the possibility to invoke probability inside the rule execution. So let's explain in more details these extensions. So if we go back to our first rules, technically speaking, these rules calls an operator, an existential operator, which is exists. We are asking the question if there exists a reimbursement of type planes inside a subscriber of a healthcare provider. That's why we introduced this auxiliary variable here, which is exist st, related to the risk type in the subscriber. Okay, and here we can directly relate exist as to the reimbursement through this reference law, but we used a divide conquer approach in order to have simplified conditional probability tables. So instead of having exist st of many parents, we only have here, for example, one parent that have another one parents, and so we can represent in the memory this conditional probability tables when we have many instances, for example, of subscriber. So the first point is to analyze the rules and enrich the model with corresponding attributes. The second one is to extend the meta model with probabilistic annotations. These annotations are kind of metadata that we add to the meta model. So, for example, we will relate the classes, we will annotate the classes with a probabilistic annotation to show that we are in front of a probabilistic class. We have type restriction annotations that shows that the type has a restricted domain. We annotate also the attributes with a definition of the conditional probability tables, and also we explicit the set of parents as we will show in the application. And finally, we have annotation to relate different classes, simple or multiple reference swap. Using this sort of annotation, we can just parse our model and generate their counterpart probabilistic relational model, which allow us to get the mapping between both of them. Now we have all the ingredients to invoke probabilistic inference within the rules inference, and to have soft rules. So instead of evaluating the attribute age and the type length, now we want to evaluate the type risk here, which is related implicitly in our model through the attribute exist st to the subscriber, and we want to have the capacity to execute the rules with if the probability of having a high type risk is more than, for example, a threshold. Here is 85, and then we raise an anomaly alert. So, as an application, we applied this concept to the IBM operational decision manager, which is the former Zeros, and we have here Zeros. It's kind of Java-like programs, and here we have the annotation that specifies that the subscriber is a probabilistic class. Here we specify for reimbursement that this is a multiple reference, and this is a special annotation which restricts the type age to a domain of 1, 2. Age type is a restricted type, and which is an int type restricted to two values. And here we have a PRM aggregator. Then we specify the type of the aggregator here. It is exists, and we specify its parents. If we go back to our example, here is an aggregator whose parents is risk. And we do the same for the other. Aggregator is just a special attribute that specify many-to-one relationship. And doing so, it avoids us to have multiple classes definition with respect to the number of instances. So we abstract the configurations. And for the system, we have two choices. Either a static definition, which is regarded as parsing the working memory and just generating the PRM system. And we have a more interesting one, which is not implemented yet, which declares the initial system by the rules, and then let the rules define incrementally our systems. So, okay. So our prototype, which is called BIS, Bayesian Insight System, is is plugged into the compilation chain. Basically, it's a series of writings. We begin with translating the business rules into the ELOG rule language, and doing a series of checking, and we can plug our prototype in this part of rule writing after getting the rule set semantic models. And in addition to this compilation API, we have an execution API that allows an interoperability between both of models. So the business rules can require or request the probabilistic engine for getting probabilistic data, and even change relations or insert new evidence on attributes, while the probabilistic engine executing the probability inference mechanism can update, can notify the business rule engine for evaluating the attributes in the working memory. So I come to the end of my presentation. To wrap up, our prototype integrates probabilistic reasoning into an object-oriented business rule management system by some models extensions that allows us to couple it with a probabilistic relational model. As a perspective, since in the level of business rules we are interested in rules, not in the process of computing, of inference computing, we want to have a general probabilistic apparatus that parameterize the whole condition. But here, it implies a very complex process of compilation to parse rules and decide which kind of attribute should we use to define the probabilistic query. Besides, since the working memory of the engine is dynamic by nature, we want the inference mechanism to be incremental or dynamic. However, the current state of inference algorithm does not support this feature. That's why we have developed an algorithm and which was presented at IPU 16 that extend the inference the probabilistic inference in the Bayesian network to have incremental aspects. So we are working on adaptation of such algorithm to the probabilistic regression model to exploit the structural information that is encoded in the system. We also talked about the aggregator and generator that are commonly present in probabilistic relational model and business rules. In our example, unfortunately, we did it manually. The next step is to automate this because we have a common base between them, and that's lead us to extend the probabilistic regression models with non-supported operators. For example, the generator from or in. And finally, since the RETI algorithm is trying to optimize the revaluation of the working memory data or objects, while taking into account the previous computation, we want to have a two-sided optimization that govern both sides, the optimization of the RETI algorithm and the updates of the the system of the probabilistic relation models. That's all. Thank you.
I have a question. What is the overhead of this framework that you are adding into the language? What is the computational overhead?
Since we are just adding annotation, it's not it's not expensive, because we externalize the inference computation to the probabilistic engine. The overhead is just to parse our working memory and to extract the probabilistic information to generate the counterpart probabilistic relational model, and it's up to the probabilistic engine to do computation, and then to answer the query with a parameter which is probability. Then we can move on and execute our rules as usual. Actually.
Okay. Well, thank you very much.
Thank you.
Our next talk is going to be by Genzu. He's going to talk about minimal objective